Okay, so I want to take a look at polynomials, and specifically three theorems that are very powerful, but also in many ways rather simple. And then we're going to look at how to use these theorems and the ideas that they bring us to write the equations of polynomials. So as we've discussed polynomials, we've spent a lot of time discussing degree, going back to factoring, and finding zeros and roots. These theorems really tie those ideas together and define some specifics that we need to know. So the first is the fundamental theorem of algebra. So we previously said that the degree of a polynomial is the maximum number of x-intercepts, or even the maximum number of zeros. Well, truth is it's the maximum number of different zeros, because this theorem is going to tell us that a polynomial of degree n has a total of n roots. They might not all be different. I'm going to have to count multiplicities in this, but I do have a total of n roots for any nth degree polynomial. Whatever the degree might be, I have that many roots. These roots, or zeros, may include rational, irrational numbers, or complex or imaginary numbers. So some examples, some simple questions I can ask based on this. Here I have f of x equals 3x to the fourth plus 14x cubed minus 2x squared minus 31x plus 10. And I want to know how many zeros must it have. Well, I can see that the highest power term is 4. So this must in fact have a total of 4 zeros. Now in terms of how would I find them, this doesn't factor by any method that we have discussed, so I would have to use something clever. A good way to start this off might be to look at the graph to at least find one or more zeros, and then we'll have other methods to possibly figure out the other zeros. What are the degree and roots for these polynomials below? Well, these are not given in the standard form. These are given more in a factored form. Well, degree and roots. For this first one right here, this goes back to when we discussed multiplicity. The roots are, if I have a factor of negative 4x, x equals 0 would give me the root of 0. X plus 5 gives me the root of negative 5. Since it is cubed, I know that means I have a multiplicity of 3. And since I have x minus 2 here, that means I have a root of 2. As we've discussed before, if I add up those multiplicities, which are 1, 1, and 3, I would find the degree. I can also think about if I multiplied these out, I would have negative 4x times x plus 5 times x plus 5 times x plus 5 times x minus 2. That would in fact be 5 x's being multiplied together, giving me a degree of 5. B is a little bit more advanced, arguably, because I am multiplying here. My different factors are two linear binomials and this quadratic trinomial right here. Well, if I think about multiplying these, I would have x times 7x times x squared. So if I did multiply those, I would have 7x to the fourth, plus a whole bunch of other stuff that I don't really need to calculate for any reason, so let's not do that. So my degree is 4, which means I should expect a total of 4 roots. Based on these factors, I can see that I have roots of 4, negative 3/7, and this last one, which cannot be factored any further, I would have to use the quadratic formula in order to factor this, or excuse me, in order to solve, to find the roots of that polynomial. And without doing it, I will just tell you that the roots of that polynomial are negative 2 plus and minus 5i. So I see this is degree 4, and I do in fact have a total of 4 roots. 4, negative 3/7, negative 2 plus 5i, and negative 2 minus 5i. So that's our first theorem, the fundamental theorem of algebra. Any polynomial of some degree has a total of that many roots, counting multiplicities. My second theorem is the factor theorem. This tells me that if I have a polynomial with some root, x equals r, then there's a certain factor, namely x minus r, that that polynomial has to have. So for example, if I had the following roots, if I had a root of 7, what factor do I have to have? Well, of course, x minus 7. What if I have a negative number? Well, x minus negative 3 would be x plus 3. What if I had a fraction? In theory, for a fraction, you could say x minus 5 halves, but usually we would say the factor is 2x minus 5. You might be able to see where that's coming from. Let me explain it a little bit more. If you think about how we would get to a solution of x equals 5 halves, where this 2 came from before that was that it was multiplied with the x. And before I had this, I would have had 2x minus 5 equals 0. And if I think about solving by factoring, that was my factor that I set equal to 0 and then solved. Lastly, rather simply, but also very importantly, if I have a root of 0, then what factor must I have? Well, if I think of it up here, x minus 0 is simply x. Whenever I have a factor of x, I will have a root of 0, and conversely, if I have a root of 0, then I have a factor of x. We have been using the converse of this theorem going back to when we learned about solving by factoring. If I give you an equation, or if we had an equation that could be factored to something like this, and I asked you to solve it, well, what do? We take each factor, set them to 0, and find our solutions. So 4 equals 0, x minus 3 equals 0, x plus 10 equals 0. Notice that's squared. And 4x plus 9 equals 0. Solve these carefully. 4 does not equal 0. That is an equation with no solution. X minus 3 equals 0 means x equals 3. If x plus 10 equals 0, then x equals negative 10. Since that was squared, I will also note that this has a multiplicity of 2. And for 4x plus 9, you can probably do this in one step, without writing out the work, I should say. But let's be careful. I would subtract 9 and divide by 4, and I can see my solutions right here are 3, negative 9/4, and negative 10 with a multiplicity of 2. Which again, calling back to the fundamental theorem of algebra, just tells me more and more that this, if I multiplied it out, would in fact be a quartic or fourth degree polynomial. So those are our two theorems. Again, they're powerful, although they seem somewhat simple in a lot of ways. Our next theorem might not seem as simple. This is called the Conjugate Root Theorem. If a polynomial has a non-real root, a plus bi, then I must also have a minus bi as a root. Notice here the difference between these two is the operation before the imaginary part of this, bi. Those two expressions, when I change the operation between or before the imaginary part, are called conjugate expressions, hence the name. Similarly, for polynomials with integer coefficients, which really is everything we see, if I have a root of a plus the square root of b, where b is not a perfect square, whether it be 5 or something that does simplify a little bit like 20, if a plus the square root of b is a root, then so is a minus the square root of b. Again, conjugate expressions. So again, bit of an odd statement, but ultimately once you understand it, it's saying something rather simple. A root of 3i implies that my polynomial must also have the root of negative 3i. And again, that makes sense when we think about the quadratic formula or solving by square roots, both of which involved having a plus or minus. If I were to have a root of negative 7 square root 5, then I must also have a root of positive 7 times the square root of 5. In a similar fashion, Negative 4 plus I square root 6, the conjugate expression, I'm going to change that operation in between and have negative 4 minus I square root 6. 2 plus the square root of 10, I would also have 2 minus the square root of 10. And the very simple 8 minus I, if I have 8 minus I as a root, what else must I have? 8 plus I. So these three theorems, again, they are a bit simple from some standpoint, but they're also very powerful. Some problems I could ask you relating to this last theorem and then using the theorems together. If I have a fifth degree polynomial that has the roots negative 8, 5 minus 2i, and the square root of 10, what are the other roots? I'm telling you it's a fifth degree polynomial, which means I should have a total of 5 roots. Well, I look at these. Negative 8 is an integer. I can have those one at a time. But here I have an imaginary number and the irrational square root of 10. So each of those comes with a partner. 5 minus 2i means I must also have 5 plus 2i. And the square root of 10 means I must also have the negative square root of 10, giving me my 5 total roots. What is the least possible degree of a polynomial if it has these roots? This is another question I could ask relating to the theorem we just discussed. 3 is an integer. Negative 9/4 is a fraction or a rational number. I can have each of these one at a time. 5 plus the square root of negative 18, though, well, I look at the square root of negative 18 and I know that can be simplified. First off, there's a negative under the radical, which means I can pull out an I. And the square root of 18, well, that's 9 times 2. The square root of 9 is 3. So the square root of negative 18 is actually 3i square root 2 if I simplify it. So if I have this funky little root here, then I must also have its conjugate 5 minus 3i square root 2. This is 5 plus 3i square root 2. I also have its conjugate, 5 minus 3i square root 2. I now know that I have a total of 4 roots. So the least possible degree is 4. Because I know that I have 4 roots. So now, once I have these theorems, once I understand that a certain root implies a certain factor, and that certain roots come with a partner, I can put these together to write equations for polynomials, knowing only the roots. In question 3, I'm asked to write a polynomial both in factored form and in standard form with the zeros 0, 7, and negative 3 with the multiplicity 2. Here I've written it as negative 3 with multiplicity 2. You might sometimes see this just with negative 3 listed twice. Both imply the same thing. The factor associated with this 0 must be squared. So if my zeros are 0, factor is x. For 7, I will have a factor of x minus 7. And negative 3 with multiplicity 2 means I'll have a factor of x plus 3, but it must be squared. So that's my factored form. That's my first answer. The question is, how do I make this into standard form? The standard form of a polynomial lacks all of these parentheses. That is to say, it is multiplied out. So what I'm going to do is some multiplication. Now bear with me, I'm going to try and use my space wisely. I'll try not to write too small. How you multiply this? There are multiple methods you can use, and the order in which you multiply the factors does not matter. I would tend to leave the x to the last because the distribution is the easiest thing to do. I would probably start by squaring x plus 3. X plus 3 squared means x plus 3 times x plus 3. So when I get this, what do I get? X squared plus 3x plus 3x. This gives me x squared plus 6x plus 9. So now I take that with the other factors I have. I need to multiply x minus 7 with this trinomial. To multiply a trinomial and a binomial, I can either do something like what I just did, splitting up and distributing, or I can make a little 2 by 3 box to keep things nice and orderly. So if I do this, x times x squared is x cubed, x times 6x is positive 6x squared, positive 9x. Of course, we've discussed these methods before, so this should be familiar. Negative 7 times 6x is negative 42x, and I get negative 63. So what do I have now? Combining my like terms, I have x cubed minus x squared. Negative 42x and positive 9x give me negative 33x minus 63. But I mustn't forget, what have I done? I first squared x plus 3. I multiplied by x minus 7. I still have an x out there to multiply. So my final answer, after doing that distribution, will be x to the fourth minus x cubed minus 33x squared minus 63x. Let's do one more example of writing in standard form, starting from factored form. This one's a bit trickier. Worth knowing, a bit trickier. What if I'm given an imaginary root? I want to find the standard form of a polynomial with the roots 5, negative 1, and 3i. I can start this off simply enough. A root of 5 comes from the factor x minus 5. A root of negative 1 comes from the factor x plus 1. And 3i. Based on our theorems, we know that 3i as a root means I must also have negative 3i as a root. And in order to write this, we start off with something that will look a bit strange. The root 3i would presumably come from the factor x minus 3i. Negative 3i would come from the factor x plus 3i. This looks strange. We have never factored like this, and we're not going to start today. In writing the standard form, I'm going to multiply these back together anyhow. So how do I do that? Well, again, I can FOIL, I can use the box, I can do any of a number of things. I can split it up and distribute the way I did up here. Also notice that this is x minus 3i times x plus 3i, or a minus b times a plus b, which we know is how you factor a difference of squares. So as I work through this, if you're thinking, maybe you'll know where this is going to end up. Right in here, I have x squared. These things cancel out, so I'll have x squared minus 9i squared. Now remember, we know that I is the square root of negative 1, which means I squared is negative 1. So this is x squared minus 9 times negative 1, or rather x squared plus 9. matter of fact, we can kind of generalize where imaginary roots, the factors that are associated with them, if I have something as simple as 3i or 4i or 10i or anything like that. But let's continue on finding the standard form of the polynomial with the given roots as we've been doing. Well, my next step would be to multiply two of the binomials. I'm going to multiply these two together. I'll leave it to you to check this work is correct. But the result you should get from multiplying x minus 5 and x plus 1 is x squared minus 4x minus 5. And now I'm left, once again, to multiply a binomial and a trinomial. The simplest way to multiply a binomial and a trinomial and keep your work neat is with the 3 by 2 box. X squared times x squared gives me x to the 4th minus 4x cubed minus 5x squared plus 9x squared minus 36x minus 45. The like terms right in here, 9x squared and negative 5x squared, give me my answer, x to the 4th minus 4x cubed plus 4x squared minus 36x minus 45. And now I have the standard form of a polynomial with these roots. I made a reference, I made a comment a minute ago, which I will go back to. 3i meant I also had a root of negative 3i. In general, bi and negative bi come from the factor x squared plus b squared, whatever that b might be. Now again, there are more problems we could do with this, more advanced problems, but this is essentially what you need to know.